In this video, I'm going to explain the concept of hypothesis testing. And I'm going to start by an example. I will link through this example the concept of hypothesis testing with the concept of confidence intervals learned in a previous unit. And then I will show in which cases these are different. So I'm going to start this section with an example. Let us read this question. Assuming a company produces flu tablets with masses that are normally distributed with a standard deviation of 0.038 grams. So the standard deviation is given. On the packs, it is claimed that the weight of a tablet is 5 grams. So the mean of the population of all tablets is 5. Of course, not each tablet is 5. We have a normally distributed population of tablets, but that's a mean weight. Now I need to check whether the standards are met or not. Does the company tell the truth? So what we do is, at the production line, the supervisor believes that the average weight of the tablets has changed. So he takes a random sample of n tablets. How is he going to check? Take n tablets and find that the mean of this sample is 4.87 grams. So the question is this 4.87 grams too low? Or do we decide that it's close enough to 5 and the company produces the correct weight of tablets? So that's what we need to decide. Let's see what we know about this problem first. Even though n is relatively small, the fact that the masses of the tablets, and I'm going to denote by x the masses of the tablets. So the masses of the tablets are normally distributed with a mean 5 and the variance 0.038 squared. We always consider that the person claiming is right. So we consider that the company produces the right weight. Now n is small indeed, but because x is normally distributed, then accordingly to central limit theorem, the sampling distribution of the mean will be normally distributed with 5, 0.038 square over 10 as a variance. Okay, so let's see how far 4.87 is on this distribution. So we need to make sure that we understand that this x bar, the mean of the samples, is not on the distribution, but is on this distribution because it represents a mean. I know that the sampling distribution of the means is normal, and this variance is smaller than the variance of the initial population. So I know that the mean is 5, which is not relevant, and then I know this is the shape. So I want to see where 4.87, it will be in this side. Where is it? Is it close to 5? Is it far from 5? So what I'm going to do is I'm going to consider that that's a really odd sample if it lies outside the 95% confidence interval. So I'm going to decide, and this is my decision, that if my 4.87 is within this 95% of all the samples, then it's a good sample and I will accept the claim that it's 5 grams a mean. But if my 4.87 it's outside, of course it's going to be on this side, I know now, but if I see that it's outside, then I decide that it's a very odd sample and it's very likely that the company actually doesn't produce a weight tablets with 5 grams. So I'm going to find the 95% confidence interval in this case. And I know from the formula which we used before, so confidence interval is in another unit, but actually you could find these points here even using the S1 statistics 1 module on this normal distribution. So I find that the confidence interval is between 4.87 minus 1.96, which is the z-score for 97.5%. So here in this you have 2.5%. Here you have 2.5% of your data because you need the 95 in the middle. So this one corresponds to a z value of 0.975. So 0.038 over square root of 10 less than the real mean, less equal than 4.87 plus 1.96 times 0.038 over square root of 10. So that's a previous unit, right? So the confidence interval lies between 4.846 and 4.894, you can check. And that's a 95% confidence interval. Now, where is my sample mean? 4.87. So 4.87 lies here. So lies within the 95% confidence interval. This means that the sample is not an odd sample. It's a normal sample. It's within the 95% confidence interval. So I will decide that actually the supervisor is not right and the company still produces the 5 grams tablets. If my sample mean would have been here or here outside, or actually, 4.87 cannot be here, it needs to be on the other side because it's smaller than the mean. So it's somewhere here. It's still within the 95% confidence interval. So we will say that at a 5% confidence level, significance level, 5% being outside, so we call the outside area significance level. So we say that at 5% significance level, we can decide that the company produces flu tablets of a weight of 5 grams. In statistics, we can never be sure, but we have enough evidence at 5% significance level. What we've done actually is hypothesis testing. Let us formalize a bit what we've done. So in hypothesis testing, we have 2 contradictory hypotheses under consideration. One hypothesis in the example above is that mean is 5, mu equals 5. We call it H0, null hypothesis. And in my case, null hypothesis is mean is 5. The other hypothesis is the alternative hypothesis. And in my case, is mean is not 5. The supervisor in this case doesn't test that the weight of the tablets is lower or higher. It just checks if it's different. That's why this is called a two-tail test. And see from the image how you have the 2 tails of the test. If it was possible to collect data from the entire population, then we know for sure which of the 2 hypotheses is correct, if we could generate all possible samples of size 10. But usually this is not possible, or it's very difficult, or it's inefficient. So as a result, we must decide which hypothesis we think is true by using the information from a random sample, one random sample. In order to avoid bias, the sample needs to be randomly chosen. So hypothesis testing is a method for deciding which of the 2 hypotheses is correct. Always we start by assuming that the null hypothesis, H0, is a correct one. After carrying out the test, this hypothesis is either accepted or rejected. In order to be clear in my mind, I will just think of H0, accept H0 or reject H0. That will be the outcome of my test. Of course, if we accept H0, it means that we will reject H1. And if we reject H0, it means that we accept H1. But I'm just thinking of H0, and then what I do with H1 automatically follows for that. So, in general, what we have is the null hypothesis, H0, which states the assumption to be tested. It's always expressed as an equality, mu equals something. Generally, it's about mu, the mean. We begin with an assumption that the null hypothesis is true, and this one refers to the status quo, what is now. And this one may or may not be rejected. We have also an alternative hypothesis, H1, which is the opposite of the null hypothesis. Can sometimes be mu not 5, which gives you a two-tailed test, or mu smaller than 5, or mu bigger than 5. Depends on the context. Now we just work with a two-tailed test. This alternative hypothesis challenges the status quo, and is generally the hypothesis that is believed or need to be proven to be true by the researcher. In my case above, I'm going to say that as a result of my test, I accept H0, because H0 is in this region, which I call acceptance region. If my sample mean will fall here, I will decide that the sample is very close to what the status quo is, what the company says. So it's not an odd sample. So in my case, the decision of my test is that I accept H0. Therefore, we can accept at the 5% significance level that the company produces flu tablets with masses of weight, or with masses of 5 grams. Always I need to express my conclusion in terms of the question and of the setting of the question. Now we will need on the next page to formalize this process. What do I need actually to show my working? I'm going to take this example, and you can pause the movie and try it by yourself first. So we've done all the calculations, and you have some time to reflect on them in light of the previous questions. The conclusion of this test is that we reject H0, and we need to refer back to the initial question, so that we will say that the jars of jam do not have a mean of 351.2. There is enough evidence at 5% significance level to reject H0, therefore to claim that the jars of jam are not filled at that weight. Here is another question that I would like you to pose and try by yourself. In this case, we are not given the mean of the sample, but we can find the mean of the sample by ourselves from the data given. Also, this will be a one-tail test, because we want to check if the amounts of fruit have higher levels of systolic blood pressure than usually for healthy young kids, so it will be a one-tail test. Just pause and try by yourself. So after analyzing the data, I'm always under H0. Okay, so what happened was that, same as before, I'm under H0. That is my sampling distribution of the mean. That's my representation of it. I want a 2% significant level, but it's a one-tail test. So it's bigger than 105, so I'm looking for 2% here. Critical value, I need to state always critical value, and it's always on the standardized normal. So I'm looking at the standardized normal. I was disappointed to see that 98%, which is this area to the left, is not in the table to find it easy. So therefore I use my calculator and I find this critical value. And then I need to see where my test statistic is with respect to critical value. But I can't compare the critical value with the mean 112, because this mean is on that distribution and the critical value is on that distribution. So I need to standardize and bring the mean of the sample to the standardized distribution so that I can compare. And that's my test statistic. That's what I test against. That's how the standardized and the parent population are related. And my test statistic is 3.388. And you see it's in this region, in the rejection region, is way far from the mean here. Therefore, I reject H0, and I state my final conclusion that at 2% significance level, the claim that young adults who don't eat healthy or whatever have higher blood pressure is rejected. So I reject H0, going back, I reject H0. Therefore, I reject that the blood pressure stays the same. Therefore, I accept that the blood pressure is higher than usual. So conclusion, people eat healthy.